All right, it's Thursday. We're back here finishing up chapter 27 today, and we're going to cover resistors in Ohm's law. So we have here an incandescent light bulb, and we have an audio volume control that you've all adjusted the volume on your car stereos. And we have its other components here called resistors. And the question is, what do all these have in common? Um, and the answer, as we will see shortly, is they rely on the fact that all materials have a property called resistance. And these all utilize resistance to current flow to perform some function in a circuit or a device. In this case, it's simple. You run current through a light bulb, and it causes this filament to get hot, and it glows, and it emits light and also a lot of heat. If any of you ever changed an incandescent bulb. Um, Audio volume control here. You adjust the volume, which adjusts the electrical resistance of the control, and then you have various resistors here, which are used to reduce the current in a circuit. So we're going to cover resistance and then a general law today called Ohm's law, which relates the current through these devices to the potential difference across the terminals. So I've pushed the due date back. I uploaded homework 9. I've pushed the due date back to Monday, the 5th of April. But there's another homework on homework 10 that's going to be coming down the pipeline and going to be due the following weekend. So I encourage you to turn this in before the 5th, get it off your plate. This chapter is on chapter 27, as you can skip section 27 too. So in the last lecture, we discussed that if you have a conductor, for example, here's a wire and it's a metal, and if there's an electric field which is generated by placing a potential difference across the two ends of the wire, this electric field pushes electrons through the material. And by definition, recall, even though we know the electrons are obviously what are moving, we define the current in the direction that positive charge is moving. And so positive charge would move from higher potential to lower. And so we define the current as going left to right in this case, from higher potential to lower, even though we really know that it's the electrons moving right to left against the field. That's the same as positive charge moving left to right. So we define the current as going from left to right. And we know that the current density we derived in the last lecture, which is the current per area, pi r square in this case, is proportional to the conductivity of the material and on how strong the electric field is that pushes the charge through the wire. And then the conductivity and the resistivity are inverses. And so we can write the current as being equal to the electric field times the area of the wire divided by the resistivity. Now we want to put this in a little more useful form. We know that the electric field is related to the potential difference, and we can measure this, right? It's the voltage across the battery, or it's the voltage produced by some other source. So we want to put this in terms of the potential difference. So if you recall back from chapter 25, the electric field magnitude along the S direction, which in this case would be along the wire, is equal to the negative of the change in potential over the change in distance. Now in this equation up here relating the current, this is the magnitude of the electric field. And so we would plug in the magnitude of this. We could ignore the minus sign here. So we can plug that in, and delta S in this case is equal to L, the length of the wire. And you plug that in and you get that the current is proportional to the potential difference across the two ends of the wire. multiplied by all this stuff in the parenthesis, and these are all constants. You have the area of the wire, you have the length, and you have the resistivity, and all of these constants combined depend only on the wire itself, and so we define all of these as the resistance of the wire, or actually the inverse. And so the resistance is the resistivity of the wire, that's a property of the material, times the length of the wire, divided by the cross-sectional area, and we denote that with the symbol R. This is what's called the resistance of the wire. And this has units from this equation here of volts per amp, and we call that unit the ohm. And we give it the symbol omega, the Greek letter omega, which is the symbol for the units of ohms. And so the resistance of this wire depends on the geometry of the wire and on the material of the wire, which affects its resistivity. So what is resistance? Well, it's just a measure of the degree to which a wire or a circuit element resists the flow of current through it. And materials that have a larger resistance resist current more, and for a given potential difference, you get less current. So if you increase the resistivity of the wire, its resistance goes up. If you make the wire longer, the resistance goes up because it takes more potential difference to push the same current through a longer wire. So longer wires have more resistance, and if your diameter of your wire is larger, you have less resistance. Okay, it's easier to push current through a larger diameter short wire than it is to push it through a long thin wire. Okay, so this resistance depends on the wire material, and it depends on the geometry. And if we plot this, so now we have what's called Ohm's law, okay, and we're going to be using this a lot. It says that the current through a wire is proportional to the potential difference divided by the wire's resistance. So now we're going to be using this a lot in the next chapter, but it's important to note that Ohm's law only works for wires, circuit elements called resistors, which are any of these things, and other components or materials where the current and the potential difference vary linearly. In other words, if you plot current versus the potential difference, Ohm's law only applies if this relationship is linear, if it's a straight line. And in here, if you look at this equation, I is equal to 1 over R delta V, the slope is 1 over R. Okay, so only materials where the current and the voltage are linearly related obey Ohm's law. Okay, here's an example of a material that, or a device that doesn't work. Okay, if we plot, here's a diode, and these are used in a circuitry. They're semiconductor materials, and if you plot current versus the voltage across a diode, it's not a straight line. Okay, this is what's called nonlinear, and we cannot use Ohm's law when analyzing diodes in circuits. They have to be linear, and so that limits us to wires, circuit elements called resistance, which we'll get into in a few minutes, and other components. So there's 3 examples that are very good in the text related to this, and I highly encourage you to work these out and to read them. Not only are they well explained and they're good examples of Ohm's law, but they're different examples of how Ohm's law is used in the biological sciences and in medical fields, in addition to physics. So Ohm's law has applicability to a large area of the sciences. So since these are well explained, I'm going to leave these for you, and we are going to go over some different examples in a few minutes. So what materials have a linear relationship between the current through them and the potential difference across them? So in other words, what devices and materials can we use Ohm's law? Well, we can use them for wires. So wires have a very low resistivity. And so as a result, since the resistance is the resistivity times L over A, unless the wires are really long or they're really small diameters, the resistance is very small in wires. In fact, it's usually under about an ohm for most wires. So when we're analyzing circuits, as we will in the next chapter, we can model the wire as a perfect wire. A perfect wire would have no resistance to current, which means R would be 0. And since the voltage drop, the potential difference across the wire is the current times the voltage, we can assume that we don't lose any voltage. There's no voltage drop across an ideal wire, okay? So in other words, we're going to neglect the small amount of resistance in most wires when we analyze circuit, and we're going to assume that the wires are ideal and they have no resistance. Okay, in the homework problems and in household wiring, you'll see that they have a small amount of resistance. So wires we can use Ohm's law for, and we're going to simply assume that the wires have 0 resistance in our circuit analysis. The second class of materials and devices are what are called resistors. And these are circuit elements that are made of materials that have poor conductivity. So in other words, the resistivity is very large. And so some examples here, back here, these are carbon elements with powdered carbon. Some of them are metal film resistors on insulating substrates. In other words, these have fixed resistances, and they're intentionally put in circuits to keep the current down, to reduce the current. Okay, and so resistors obey Ohm's law. We'll be doing more with them. Resistors, the volume control is an element, on your car stereo is an example of a resistor. The tungsten filament in an incandescent bulb is used. And so typical values of resistors range from 10 ohms to 10 mega ohms, where mega means 10 to the 6. So this would be 10 to the 7 ohms. So we're going to analyze circuits that have various resistors in them in the next chapter. Insulators obey Ohm's law, like plastic, glass, air, except they have such high resistances because they don't conduct current that we can, for all practical purposes, assume that these materials have infinite resistance. And by Ohm's law, if they have infinite resistance, the denominator is infinity, you don't get any current through them, or for all practical purposes, the current is 0. So these are the 3 types of classes of materials and devices that do obey Ohm's law, and we can use Ohm's law to analyze their behavior. So something has to push the current through these wires and these resistors, and one common source, we've already discussed this before, is the battery, right? The battery is used, remember, you have a chemical reaction in here that pushes positive charge. It separates the positive and negative charge from this plate and shoves it over to the positive plate. So you get a separation of positive and negative charge, which creates an electric field. And that electric field pushes current through the wire. And by definition, the current goes from higher potential to lower potential. Batteries are ohmic. In other words, they obey Ohm's law. Okay, if the delta V is the voltage difference between the terminals, the current through the battery depends on this potential difference. and on the resistance of the battery. In other words, the battery can't supply infinite current. It has a small amount of resistance that you'll calculate in one of your homework problems. It's typically less than an ohm, but as batteries age, they can supply less current. Their resistance builds up as the chemical paste starts to wear down. It starts to get used up. And so over time, the battery voltage might stay close to the same, but its ability to supply current decreases as its resistance goes down. So batteries also obey Ohm's law. Here's a simple circuit that we're going to qualitatively analyze here. So you have a battery right here, and here's the positive terminal, here's the negative terminal, and if it's an ideal battery, it doesn't have any resistance, and its voltage across here is just its EMF, but just you can think of it as just delta V. Okay, and remember that Kirchhoff's voltage law, the loop law, says that the sum of the voltages around the loop have to add up to be zero. So let's start here. If we go from the negative terminal to the positive terminal of the battery, we gain potential. And at the positive terminal, the potential at this point relative to the negative terminal is delta V battery. Okay. Now, if the wire's perfect, we don't lose any voltage because the resistance of an ideal wire is zero, and so we don't lose any voltage across there up to this point, and so we're still at a potential delta V battery. We're still at a potential V battery relative to the negative terminal. Now we're going to drop voltage going across the resistor. We're going from positive to negative, right? And if current goes through a resistor, Ohm's law, delta V is equal to IR, said that we will drop voltage across here. Okay? And so at this point we're down, we don't drop any more voltage through this because it's an ideal wire. So all of the voltage gained in going across the battery, all the voltage produced by the battery is used up by the resistor, and that's Kirchhoff's loop law. So by the time we get back to this point, we're back down to V equals zero relative to the negative terminal. And you don't get any more voltage drop across here because it's a perfect wire, and a perfect wire has zero resistance, and so Ohm's law says it doesn't drop any voltage. So in a nutshell, in the circuits that we're going to be analyzing next chapter, which are more complicated, we're going to assume zero resistance of the wires so they don't drop any voltage. And we're going to apply Kirchhoff's loop law, which says that the voltage drops across the loop have to add up to be zero. In other words, what's gained in going across the battery has to be lost in going through these resistors. So we'll be doing more of that in the next chapter. Let's end with a couple examples here. We'll end the chapter. This chapter, like I said, is much easier, I think, than your last few chapters. So you have 5 wires right here. They're all made of the same material, so they have the same resistivity, but they have different diameters and they have different lengths. And so what we want to do is we want to rank the resistance of these wires from highest to lowest. Okay, so what we need to do is we need to find a mathematical equation which relates resistance to the wire dimensions and to the resistivity. And that's just the resistance is equal to the resistivity times the length divided by the area. And the area, since the cross section is a circle, is just pi r squared. So wire A has a length L, and it has a radius r, and so we plug that in, and it's just rho, which is the resistivity, times L over pi r squared. Now wire B, same length, but we double the radius, or we double the diameter. It's the same thing. And we put in 2R instead of R, and we see that the resistance is now only 1/4 of the resistance of wire A. So in other words, you double the diameter, you only have 1/4 of the resistance, which means you could push 4 times more current through wire B than wire A if we hooked up the same battery across both of them. Okay. Wire C has twice the length and twice the radius, so you might think, oh, well, it has the same resistance as A. Well, let's plug it in. You plug in 2L for the length, you plug in 2R for the radius, and we see that since the radius is squared, that has a larger effect than the longer length. Wire C only has half of the resistance of wire A. Then you can go on to wire D. It has twice the length as A in the same radius, so we plug that in, and it has twice the resistance because the resistance is linearly proportional to length. You double the length, you double the resistance. That's why these longer extension cords have more resistance than shorter extension cords. Okay. Wire E, we have 4 times the length of wire A and twice the radius, and we plug that in, and it ends up having the same resistance as A. And so when we rank these, wire D has the largest resistance, followed by A and E are equal, followed by C, and followed by B. So you should be able to do this on an exam or a quiz. You should be able to understand how the resistance of the wire depends on the length, the diameter, and also, not in this problem, but I could ask you I could have different resistivity for the 3 wires and ask you to compare resistance there too. Okay. Let's do another example. Let's calculate the resistance of a couple different wires here, a couple different devices. So the first one, we have a 2-meter long gold wire, so it's about 6.5 feet long, and it's about 0.2 millimeters in diameter. And you can look up in the table in chapter 27, I think it's table 27.1 or 2, it's one of those, that the resistivity of gold is 2.4 times 10 to the 8th, negative 8th ohms meters. Okay? So if you know the resistivity and you know the length, and diameter gives you area, we can plug all those in, and we get that a gold wire that's 0.2 millimeter diameter and 2 meters long has a resistance of about 1.5 ohms. Okay. We can do the same thing for carbon, which is what resistors are made out of. Carbon is also what pencils are made out of, the lead. Carbon, I mean. And so if you have a 10 centimeter long piece of carbon, and it has a square cross section, 1 millimeter by 1 millimeter, we can plug in the resistivity of carbon, which you see is much higher than that of gold, and you see that the resistance is 3.5 ohms. Okay? So we've just made a 3.5 ohm resistor out of carbon. So you should, again, here, it's just another example of calculating resistance given the material properties, the resistivity, and the geometry. Let's finish it off with one more example. This one's a pretty easy one, but one you should be able to do. So suppose that for a given material, we vary the potential difference, or we vary the current through it, and we measure the potential difference, and we get a linear relationship. Okay, so it's linear, which means that we can use Ohm's law, right? I is delta V over R, which means that R is delta V over I. And so, in other words, the inverse of this slope, because the slope here is I over delta V, that's the slope, the inverse of this slope gives you the resistance. Okay, and the slope is 1 over 50. It's 1/50th of an amp per volt, and the resistance is the inverse, which means that the resistance of this material is 50 ohms. Okay, so you should be able to take a plot of current versus potential difference. You should be able to calculate resistance. And if you're given resistance, I could further ask you what the resistivity is if I give you the length in the cross-sectional area. So that's pretty much it. This is a pretty short chapter. Remember, homework 9 is due Monday the 5th at 11:59 p.m. It's a short homework. It's only 8 problems, and most of them are very short. All of them are, I think. So this should be a pretty straightforward assignment compared to some of them you did. So have a good weekend, and we will see you next week where we'll start chapter 20.